So even though you have used the fundamental theorem in other courses, as I said, let's recap where we're at in terms of integrals from the theory point of view, which we have seen in this course. Okay. So far we've seen indefinite integrals. Well, these are just antiderivatives, right? We start from saying, okay, if we have a function and we know its derivative, then we can compute the antiderivative of the second function by simply adding a c, an arbitrary constant, right? So this is really more of a, seems like a very technical, little technical tool that says, okay, well now we computed derivatives, how can we go backwards? Now, on the other hand, we have seen definite integrals in the last couple of classes, and they were defined just as areas. The definite integral of a function f of x between a and b is the limit as n approaches infinity of the sum from 1 to n of f of xi delta x. And if we can compute that one, we're lucky, right? So this is just a definition that gives us sort of a conceptual idea of what an area looks like. Okay? But if you notice, these two integrals so far are really only connected in the symbol that we use, the log s, and the name integral. But one deals with derivatives and antiderivatives, one deals with areas and summations and limits, right? So how are they actually related? Now, in order to see that, which is of course what the FTC talks about, oh, by the way, I will refer to the fundamental theorem of calculus as the FTC for one reason. One, it's shorter. The other one is that it's so important that it does deserve an acronym that people can use on a regular basis. All right, so before showing you what the theorem actually says, I need to introduce a little tool which is quite simple but quite important, just like the FTC. So here is the thing that we need to construct in order to have a look at this fundamental theorem. The idea is the following. Let's say that we have a function and we have a point in its domain. Okay. Now, in fact, for what's going to happen next, we're going to use basically continuous functions, but this definition doesn't really require the function to be continuous. Now, what I'm going to do is I'm going to consider what I call the area function. This is a function that describes how the area under this curve changes as I pick different points, different endpoints. Okay? So what I'm going to say is the area function at x is going to be constructed as follows. First of all, I pick my x on the x-axis. Then I look at the section of the curve which is between a and x, and I look at the area which is bounded by the x-axis, the two vertical lines at a and x, and the function f of x on top. So of course you recognize that that is exactly what we called the definite integral of the function from a to x. Now notice that in this integral now, I'm not saying the integral of f of x dx. Why? Because now I have two things, t and x, that really refer to the same quantity, namely something on the x-axis, okay? But they're playing different roles. I want my x, the traditional variable, to denote the endpoint of my region. And therefore, if I want to use the same x in a different as part of the integration, I need to call it something else. So t and x refer to the same quantity but with different roles. Keep that in mind because this might become a little bit of a tricky point later on. Because on the one hand we have to remember that these are really the same thing, the same kind of quantity. On the other hand, we're looking at them in a different way. One, t, is the variable when we construct the integral. The other one, x, is a variable in the sense of being a variable as far as the area function is concerned. Now let's see how we're going to use this area function.